All right, so today we are going to learn about relative velocity. I'm sure you have some notion of the concept already, and it's a relatively easier lesson in the sense that it's not that math heavy, but it may be a little bit conceptually challenging to understand what relative velocity is. But once you get the gist of the concept, it's beautiful. You really like it. Very useful for doing problems, and also is going to be very helpful when you take modern physics next year. And with that, we'll start learning about relative velocity. So let's start with a simple example, and let me try to give a context um, about the word relative here. So let's say we have a point somewhere here. Now the question is, we want to know the height of this point. How high is this point? There are several answers. We could measure the height of this point from an arbitrary imaginary axis that I draw here on the board. Exactly this, physically this position. And then this would be the height of this point. But I could also take the reference of the base of the board, the blackboard, right? But we can also measure the height of this point from the floor of this room, right? But why, well, why not from the ground floor of this building, or the ground outside the building, or let's say we choose the sea level and we measure it from sea level. So in physics, we almost always measure quantities with reference to something, with reference to a point, with reference to a frame of reference. So for example, if you're measuring position, you're always measuring the position from a reference to some frame, a reference to a coordinate system, or reference to a point. For example, when you say Karachi is far away, it's meaningless because Karachi is not, when you're standing in Sakkar and you say Karachi is far away, and then you're in Multan and you say Karachi is far away, and then you're in Lahore and you say Karachi is far away, all three things do not mean the same thing. So it means, so you have to talk about the distance from these cities to Karachi. And this is going to be different, of course. So what the point is that we always measure distances with reference to a point, with reference to a coordinate system. So that is what relative means in the notion in relative velocity or relative position. So in physics, when it comes relative, it means relative to something, with respect to something. So this is the height of this point P relative to the this line on the board. This is the height of this object from the base of the blackboard, and this is the height of this point relative to the floor of this room, and then this is the height of this point relative to the ground floor of the building. Or then, and that is why because positions, heights, and lengths and distances are measured with respect to something. That is why you see the peak heights or elevations in geography and other, or in weather reports. They are reported with respect to sea level, and also the pressures are reported with respect to sea level, because sea level is relatively a common reference globally. That's why we use sea level, so that everybody understands what a peak being 8,000 meters high means. Okay, and it should mean the same. That's why I used common references. So that is the case with relative position. So is the case with relative velocity. So when we measure velocity of an object, and so far the velocity we have been talking about, we have always been measuring those velocities with respect to an observer or a laboratory which was stationary. So whenever we talked about velocity in our lessons before, it always meant that the person who was measuring that speed, it was us, it was the lab, it was the point of observation. And then we were measuring the velocity of an object moving at certain velocity. So it was always a coordinate system attached to ourselves. And this is how we were measuring the velocity. But so this velocity was relative already, but it was relative to us. And it was, since it was obvious, we never made this, and there was only one observer and one object, or two objects, but always one observer. So we never really need to introduce the concept of relative velocity. But let's say if you have two objects and both of them are moving with two different velocities, you don't really need to introduce the concept of relative velocity so long as you're just dealing with the velocity with respect to this observer in this coordinate system. If you're looking at the velocity in this coordinate system, we don't need to worry about it. And this line means nothing. And when we are looking at the velocity of another object from our frame of reference, from our point of view, then this does not matter. But when two objects are moving and we are looking at them, but we also want to have an idea of what happens when you measure the velocity of this object B while sitting on A, or while sitting on B, when you measure the velocity of A. That is when the concept of relative velocity becomes very important. But the important point is that relative velocity is when you measure a velocity with reference to some point, with reference to, and it can be a moving frame. So far we have been actually in physics, strictly speaking, there is no notion of moving or stationary. We are not stationary. Things are stationary with respect to us. Things are stationary with respect to this building. Things are stationary with respect to Earth. But then Earth itself is not stationary. We are not stationary. We are moving with respect to Sun. And then Sun is moving with respect to other galaxies. So there is no absolute rest position, absolute rest. So that is why we always have to think about motion in relative terms.
तो सर हम ये कह सकते हैं कि मतलब जब हम लोग अभी तक जब मतलब जो भी मैकेनिक्स वगैरह कर रहे थे उसमें वी हैव बीन टेकिंग रिलेटिव वेलोसिटी और इसमें जिस पॉइंट से हम मेजर कर रहे हैं वो ओरिजिन है, इस सेंस में हम कंसीडर कर सकते हैं उसको. बिल्कुल
बिल्कुल यही हम करते हैं. That's how we have been dealing. So we have always been taking origin on sitting on ourselves and looking at the velocity. Okay, so it was relative to, so when for example I am not stationary, I'm moving with respect to the position of Sun, right? So we were just setting the origin there and taking this whole thing, our labs, our the room we are sitting in, to be at zero velocity, and then measuring that's why at some point you would be introduced to a lab frame of reference. That is what lab frame of reference means. That you take a frame of reference and set its position to be, and it set it to be at the origin, and then you measure the rest of the quantities with respect to it, right? So, but let me introduce it in a more formal way. So let's say that we have a car. We'll slowly build on this example. The two cars moving in a straight line. They're just standing, not moving at the moment. And then we have an observer, right? And now we set up a coordinate system right where the observer is. All right. So this is our x-axis, and this is our y-axis. Now, the position vector, let's call the observer A, and this called the car B and the car C. Okay. Now the position there is a position vector from A to B. So the position of car B with respect to the frame of reference or this observer which sits at the origin, we can write it as RAB. Okay. So RAB means the position of car B with respect to the observer A. That's the notation that I'm going to use in this lesson. So then there is a position vector from observer A to car C. The position of car C with respect to observer A, and you can write this as RAC. But then we can set up another coordinate system here where the car B is and call it X prime, right? And Y prime. So you can measure the position of car. The car has certain distance from C, has certain distance from B. So there would be a position vector going from B to C. So car C has position relative to B. It's very simple. Let's say if the car C is 200 meters away from us and car B is from this position and car B is 50 meters away from us, so then this distance is 150 meters. That would be the position of car relative to B. And we don't really need to, if the experiment requires that we focus our attention on this point of the problem, we don't really need to have the observer. You can just set the origin here and just look at this part of the problem. Now always do that. So then the vector are BC, all right? And you can also write from these vectors that R BC is simply R AC minus R AB. Is it clear to everyone? Just take this vector RAC and subtracted the vector RAB from it, you will get the vector BC. Is that correct? So this is the relative position. How do you get the relative position of car C with respect to B? This is the relative position of car C with respect to B. If you know the position of the both cars relative to a third point, you just take a difference. This is very important. Do you get it? So we know the positions of these cars B and C with respect to a third point A, and you take the difference of the two, and that gives you the position of the car C with respect to B, and it's actually the same. You could just invert the problem. You could look at the position of the car C with respect to A as well. Just probably need to change the subtraction, and then you will get a vector in this direction. So, but essentially is the difference of the position of these two cars with respect to a third observation point, and that gives you the relative position. Since these cars are not moving, so if I try to calculate the velocity of car B with respect to A, it would be this quantity. The velocity of car C with respect to A would be this quantity, and the relative velocity between the two cars would be this quantity. But if I take the derivative, this is going to be 0 because nothing is moving. VBC, VAC. So let's go to the next example, okay? Before I complete it. This was about the position. I hope you get it. I'll just rewrite the vector and then make a short diagram, just points B, C, and A. RAB, RAC and RBC, right? And the vector equation that we had is RBC RAC minus RAB, right? Now let's say that this car C is moving with some constant speed. Okay, car C is moving, and the rest, the B and observer are there. So now the vector, let's see which of the vectors would be now time dependent, would change in time, and which of the vectors would not change in time. So if car C is moving, would RBC change? In chat, please. Yes. So let's denote that with a time dependence. And RBC changes with time. Would RAC change in time? In chat again. Yes. So let's say that it is changing in time. Then would RAB change in time? In chat, please. No, very good. So let's denote that with 0. So it would remain the same as it was at the time of the start of the observation, at time 0. So now let's take the derivative of everything, a time derivative across these vectors. If you take the time derivative, can I then write that this is nothing but the velocity BC? And I'll explain what BC means, okay? And velocity AC and minus 0, because this is not changing with respect to time, right? Now this is the position vector. Well, let's look at this one. This is the position vector of car C with respect to observer A. Okay. So if the rate of change of that position vector, which is the position, again, the position of car C with respect to A, is nothing but the velocity of the object C with respect to A. Or in other words, the velocity of car C as it is being measured by this observer A. Because B is not moving. They are not moving in this case. Both. Just C is moving. Okay. So what does that mean? It means if I am looking at a car and measuring its position, its speed, its velocity, and somebody a few meters down the road is again standing and looking at the same car and measuring its position, its velocity, what do we both measure? What velocities?
Same value.
Same velocities. Both of the observations would be the same. Okay, so this is very important. So as long as both of the observers are stationary with respect to each other, measuring the velocity of a third object, the both of them would measure the same velocity. Okay, let's make it a bit more complicated now. Now let's say both cars are moving. Car B is moving and car C is moving. But let's say that they are moving with the same speed. So this car is moving with the same speed as this car. All right. And now let's look at our vector example again. So this is the vector. All right. Now I'm going to write the time dependence one more time. Now RBC, is it changing? More people? I want more answers. Okay, I've got a couple of yeses and I want to address that. That's fine. So both cars are moving with respect to each other. Sorry, both cars are moving with the same speed. So if we observe them 15 minutes later, if they are 100 meters apart and they're moving with the same speed, if we look at them 15 minutes later, what is going to be the distance between the two? The same, right? So the distance is not changing. If the distance between the two cars is not changing, it means the position vector with of the two cars with respect to each other is not changing, which is RBC, this position vector. Both cars are moving right at the exact same velocity. So if the position vector is not changing with time, it is the same as we started the race or the motion. How about the other two vectors? RAC, of course, is changing because observer is standing, both of the cars moving. So RAC and RAB, both of them are changing. There is a minus sign here. All right. Now, if we take the derivative on every side, so this is going to be 0 because it's not changing with time. RAC, so this would become, sorry, VAC. And again, the definition, VAC means the velocity of object C as observed by the observer A minus velocity of the object B as observed by the observer A. All right. So what does that mean?
Velocity AC to velocity AB.
जी ये अब इसका ये मतलब है दो चीजें हमें यहाँ से पता चली हैं. RAC is equal to RAB. If two objects are moving, it's now the inverted problem. We had two observers and one object moving, and we found that the both observers are going to measure the same velocity for that object. Now it's interesting, it's reversed. We have one observer standing and two objects moving at the same velocity. And although they are moving at different places in space, they're moving at the same velocity. So the stationary observer measures, A measures the velocity of C, and it turns out to be equal to the A measures velocity of B. It's common sense, but I just wanted to formalize it. So is this clear?
सर आर वी होना
तो ये वी नहीं होएगा, आपने आर लिखा हुआ है
Oh,
डिस्टेंस का.
sorry. Oh, yes.
सर जी ये चीज तो आपने हमें पहले बता दी थी, मतलब
नहीं, पहले
क्वेश्चन
पिछली में हमने ये देखा कि two stationary observers are looking at one object. They're stationary with respect to each other. Now we have one observer stationary and two cars moving at the same speed. So they both are moving with respect to the observer, but they are not. They have constant speed with respect to each other. एक तो ये conclusion है. दूसरा ये है कि VBC is 0 as expected. Now VBC is the velocity of car C as measured by while sitting on car B. So their relative, that is the relative velocity.
यस सर, ये कंक्लूजन काम कर.
Okay. So the velocity of the car C with respect to B measured when they are moving at the same speed is 0. And we are getting that. But this is also very important, that moving observers looking at two moving cars and two stationary observers looking at one moving car or one stationary observer looking at two moving cars, the answers would be same in these two cases. Because both cars are moving at the same speed, there is no relative speed. They are not moving relative to each other. As if you can imagine, you can just get on top of one car and say that this car is stationary, not moving. Just shift that to the origin. And that would mean that this car is not moving. And the way to test it is that the distance between the two would never change. So that is why motion and being stationary does not make sense unless you define a frame of reference. Motion can only be quantified when you define a frame of reference and a point then starts changing its distance with respect to that point of reference. So if you take the B as your point of reference, the distance of C from B would never change even if they are moving both 100 kilometers per hour. Okay, now the third case. So you have to just memorize this figure now or read your notes because I'm not going to draw a third time. I'm just going to write the vectors. RBC is equal to RAC minus RAB. All right. So now the situation is that both cars are moving, but both of them are moving with a different speed or different velocity. All right. So now all three vectors are changing with time. The position of the car B or car C with respect to B is changing because one is speeding and the other one is going faster and the other is going slower. As time passes, the distance between the two would become larger and larger. Okay. It depends on who is ahead and who is behind. If the slower car is ahead and the faster car is behind, the distance would shrink. And if the faster car is ahead and the slower car is behind, then the distance would expand. Okay. So now all these vectors, three vectors are changing with respect to time. So if you take a time derivative, you get VBC equals VAC minus VAB. All right. Now, what this means is that if you have two objects moving at two different speeds, and you know their speeds with respect to a third point. So if you know the speed of A, if you know the speed of B and C, although both of them are different with respect to A, if you know these two speeds, VAB or velocities and VAC, and they're moving different at different speeds. Both are moving at different speeds. They're moving at different speed. Their relative velocity, there is velocity with respect to each other, can be obtained by just subtracting these two quantities, VAB and VAC. The velocities of the two objects as measured by a stationary third observer. If you take the difference of those velocities, you get what? The relative velocity, the velocity between these two objects. So let's do a quick example if I have that page here. Yes. So let's apply this concept. Let's say that we have a car that is going 120 kilometers an hour. Let's say the car, this is a speeder. And then there is a police officer. Now she notices the car so let's say that, yes, she notices that some violation, there is probably the tail light is broken. And then she wants to stop the speeder. Now police officer, while she gets ready to start chasing this car, this car has already covered a distance of 2 kilometers. All right. Then once by the time she has reached 140 kilometers, let's say, by the time she has 140 kilometers per hour speed, the distance between the two cars is 2 kilometers. How long she has to chase the speeder to get to them? How do we get that? How do we solve this problem?
The relative velocity.
Relative velocity. So now this speed of the police officer is with respect to a stationary observer, as being observed with nobody is observing there, but this speed is with respect to the ground, and ground is there, is stationary. So 140 kilometers an hour on your speedometer is with respect to the ground. There are all kinds of other velocity components that have been taken out by shifting the origin on Earth. Otherwise, if you're moving 140 kilometers an hour on the surface of Earth, if you add the spinning of the Earth, the rotation of the spinning motion of Earth, then there would be additional velocity. If you add the rotation of Earth, there would be more velocity. Then if you add the motion of sun, there would be more velocity. So we have taken all those components out by shifting the origin to the origin or coordinate system's origin on Earth. So this is the ground speed. This is the speed with respect to ground. And this is the speed with respect to ground. So if we subtract these two velocities, the relative speed or the relative velocity, this is ours, is 20 kilometers an hour. All right. And then since the distance between them is 2 kilometers, so we just use this simple formula, S is equal to VT. And we already know T and the relative velocity. Sorry, we already know the relative velocity and the distance. We need to find how long does she have to chase. So if you do S over V, this is 2 over 20 or 1/10 of an hour, which should be 6 minutes. So it would take her 6 minutes of chasing to get to the speeder. So you see, this problem becomes very simple if we use the concept of relative velocity. So the relative velocity is the difference between the two velocities, right? Any questions so far?
Yes, sir. सर एक वैसे कन्वेंशन रिलेटेड क्वेश्चन है सर, लेकिन हमने जिस तरह पिछले एग्जांपल में C की वेलोसिटी में से B की वेलोसिटी माइनस की थी, मतलब हम जब उसको लिखते थे तो हम मतलब B वेलोसिटी ऑफ B विद रिस्पेक्ट टू C लिखते थे। सर हम जो मतलब उसमें फर्क पड़ता होगा ना जब हम लिख रहे हैं कि हम किसकी वेलोसिटी को किस में से माइनस कर रहे हैं, तो विद रिस्पेक्ट टू में
नहीं वो फर्क नहीं पड़ता है ना, वो फर्क नहीं पड़ता। ये तो प्रॉब्लम की नेचर इसलिए है ना कि ये हमने इसकी वेलोसिटी को इससे सब्ट्रैक्ट कर लिया है so that we get a positive number, but it does not really make a difference which velocity. Relative velocity is just you could otherwise तो फिर physics में बड़े मसाइल हो जाएं। If it becomes observation, if you were observing the speed of this car while sitting on this car, you will get 20 kilometers an hour.
लेकिन अगर मैं दूसरी गाड़ी में बैठूं तो -20 किलोमीटर पर आवर नहीं होना चाहिए। मेरा पूछने का मेन मकसद यही है कि अगर मैं जिस ऊपर आपने वो इक्वेशन लिखी हुई है VBC = VAC - VAB, अगर मैं वहां पर VCB कर दूं तो वो मतलब साइन रिवर्स नहीं होना चाहिए, मैं ये पूछ रहा हूं।
हाँ वही तो मैं बता रहा हूँ ना कि साइन फिर देन द डिस्टेंस की साइन भी चेंज हो जाएगी, आपके टाइम की साइन नहीं मसला होगा। Because if you set your it depends on the frame of reference, ठीक है ना? If your frame of reference is this way, then or this way, so then you will have the distance vector change its sign as well. Yeah.
ठीक हो गया।
So it doesn't really depend on which velocity you subtract from which velocity.
सही, वैसे कुछ ज्यादा ही सिंपल नहीं था
जी?
ये कुछ ज्यादा ही सिंपल नहीं था।
Yes.
ये सवाल
सेम सर, वो पता नहीं इतना क्रेडिट दिया जाता है।
Okay, that was the chat forum or WhatsApp or TikTok, not here. Please. Excuse me, who is this? No cross discussion, please. So now we have another example. It's a slightly just to mathematize the situation because it seems that it's too simple what we have. So now we have another interesting example. So we have a rain droplet and it's dropping down, free falling. And then we have an observer who is measuring its speed, right, on ground.
Sir, where are you writing?
All right, so we have a air droplet, oh sorry, a rain droplet, okay, and it's falling, it's free falling, and then we have an observer who is standing here, and as looking at this droplet and measuring its speed or measuring its velocity, and then we have a car. And we have an observer in this car, which is moving at a certain speed in this direction, in the horizontal direction, right? And now we are measuring its speed from the car as well, all right? And then this observer is also measuring the speed of the car, all right? Now this is the situation, but before I elaborate on the situation, if something is vertically dropping and in front of you and you are traveling towards it, it appears slanted. So because if you look at this distance and this distance, now this droplet is moving. So this is the distance. If you look at the projection, this is the distance between the droplet's ground position and us, the car, and this is the distance between the droplet and the ground. And if you are moving towards this point, both of these vectors are decreasing. This vector is decreasing and this vector is decreasing. Both of these vectors are decreasing. So it looks as if this droplet actually, if we look, as if it is slanting towards us, as if from this point of view, it looks as if it is moving towards us along the diagonal, right?
सर आप प्लीज ये दोबारा एक्सप्लेन कर सकते हैं, मुझे सही है समझ नहीं आया.
So if something is dropping before you, right, like this, and while this object is dropping, you're always also traveling towards it, you're moving closer to it, there are two distance vectors. This is the distance between the you and the object, right? Isn't it?
Yes.
And it has two components. This component, the horizontal component, and the vertical component. And you see
Yes.
the object is dropping and you are moving in this direction. Both of these vectors are decreasing. Okay, so it gives you the perception as if the object is moving towards you, is slanting towards you. Okay.
सर हमने एक स्टेशनरी ऑब्जर्वर लिया है और एक मूविंग ऑब्जर्वर लिया है.
Yes, this is a moving observer. And this is a stationary observer. So now you can write the velocities of these objects in a frame of reference. Let's say we could choose this let me just label them first correctly. So let's call the observer A, and let's call the droplet C, and the moving observer B. Stationary observer A, moving observer B, and the droplet is C. And then we can choose the origin here. This is Y, this is positive x-axis. Okay. Now what would be the velocity vector of the moving observer? Let's call it VAB. So the velocity vector of the moving observer with respect to the stationary observer, because that's what AB means. As A measures the position of velocity of B, that would be what? VAB scalar EX. No, sorry. Shouldn't be like that. I think I have made a mistake with the labels. Anyway, we should do that according to these labels. So what would be VAB? VAB EX minus, right? Oh no, positive, because we are going in the positive x-axis. The point direction of, although we are in the negative, on the negative side of the origin, but we are going in that direction. We're going positive, so we're going in the positive direction of the x-axis. Okay, then we have VAC. That is the velocity measured by the observer A of C. Okay, and there is only y component of that. VAC EY. Now this is against this is in the opposite direction of the negative direction of the x-axis is falling down, while my
Sir,
positive
हमने A लिख
y-axis.
दिया।
Oh yes. VAC EY, right? And now we need to write the velocity vector of C as observed by B. So the velocity vector of C as observed by B would have two components. Because we are moving closer to the C, it is, you can translate it as if C is moving closer to us and C is also moving down. So C, while looked at from this point, C has two components of motion, the vertically downwards and the horizontally leftwards. All right. So we have to resolve that. And let's say that this angle theta, this is the angle theta that the horizontal component, the vertical component of the droplet makes with the line of observation. Okay. So then the velocity vector would have two components.
सर VC भी नहीं होएगा,
जी
VC भी नहीं हो सकता।
हो सकता है, that doesn't make a difference. But let's write it VBC, okay? VBC sine theta EX. And now this would be negative because the velocity of the object, I understand the confusion, although we are moving in the positive X direction, but we say we are not moving. We are just standing. It's the droplet that is coming to us at the same speed, our speed. We transfer our speed to the droplet, the horizontal speed. Then the droplet speed becomes negative because it's pointing in this direction. The vertical component of the droplet is, of course, independent of our motion. B cosine theta EY. And ये भी negative होगा because it's falling downwards. Okay. Now what the objective is this, that we need to find out the relationship between our speed as being observed by the stationary observer and the speed of the droplet with respect to us. So you have now these three velocities, and again I forgot to write the velocity vectors. If I could write, so you could draw a vector from A to B, A to C, and B to C. So this would be RBC, this would be RAB, and this would be R AC. And as you can see, I can sum RAB plus RBC equals, RAB plus RBC equals RAC, right? So if you imagine that you are taking a derivative of this equation, you will get VAB plus VBC equals VAC, right? So now if you plug these values into this equation and compare the components, so we first compare the X component. There's only the two X components. So VBC on this side and VAB on this side, and VAC, the X component is 0 of VAC, okay? The X component of VAB is this, the X component of VBC is this, and the X component of VAC is 0. So this turns out to be VAB equals, no, minus VBC sine theta equals 0. So we have basically found VAB is equal VBC sine theta. So one of the relationships. And then if
So
you
ये
compare,
picture दिखा देंगे ये इधर कैसे पहुंचे मैं देख
देखें ये वेक्टर है RAB इस तरह, ये वेक्टर है RBC, ठीक है? इन दोनों को सम करें तो क्या होगा? आपको ये वेक्टर मिल जाएगा RAC,
जी सर
ठीक है? तो ये मैंने लिखा है टॉप पे, ये पोजीशन वेक्टर्स हैं, ये चेंज हो रहे हैं टाइम के साथ, इनका डेरिवेटिव लेंगे तो आपको क्या मिल जाएगा? Velocity of the object B as measured from A, velocity of the object C as measured from B, velocity of the object C as measured from A. Okay? And now
yes sir
अब इस इक्वेशन में इन वेक्टर्स की वैल्यूज डाल देंगे, वेक्टर्स जो लिखे हुए हैं तीनों।
सर लेकिन आप बता सकते हैं कि हम बीबीसी में क्यों कंपोनेंट्स लेते हैं, बीएसी में नहीं लेते?
बिकॉज ये देखें ना,
हॉरिजॉन्टल
ये VAC में है ही नहीं कंपोनेंट, ये देखें ना, अगर आप, हाँ ठीक है, अच्छा सवाल है ये देखें ना, आप यहाँ से मेजर कर रहे हैं, ठीक है, ये यहाँ से ड्रॉपलेट की स्पीड मेजर कर रहे हैं, वेलोसिटी, there is no this position is not changing, this distance is not changing, the ground point, the ground position of the droplet and the observer is not changing, so there is no change in velocity, relative velocity between the droplet and the observer in the horizontal direction, only the vertical component is changing. So इसलिए VAC is only VAC negative in the negative direction of the y-axis, इसमें x component है ही नहीं, ठीक है? This side we have two components when we measure it from the car, because this distance, the distance between the ground position of the particle, the object, and the car is changing, so we have both components, and the vertical component is changing.
Sir,
Alright.
why does minus VBC sine theta EX have a negative sign?
Yes, it has a negative sign because we are getting closer. ठीक है ना, तो जो velocity का component है वो is pointing in this direction.
Okay, thank you.
ठीक है, तो इसकी जो droplet की velocity इस कार से measure होगी ना, वो I don't know, the colors are not clear. So these are the two components. All right, and now remember the coordinate system is this. This is the choice of coordinate system. Okay, now in this coordinate system, this component is negative. In this coordinate system, this component is also negative. So here, negative. राइट। अब ये तीन आपके पास वेक्टर्स हैं, 1 2 3। अब ये इसको यहां सब्स्टिट्यूट कर दें, ठीक है। वंस यू सब्स्टिट्यूट, एंड ये मैंने पहले भी बताया था, व्हेनेवर वी हैव अ वेक्टर इक्वेशन दैट मींस द corresponding components are equal। तो अब ये देखें, VAB का x कंपोनेंट यहां आ जाएगा और VBC का x कंपोनेंट यहां आ जाएगा, ठीक है। इक्वेशन एक ही आएगी। और VAC का तो x कंपोनेंट है ही नहीं, तो I'll get one of the equations would look like this. This is the x component comparison, the x component, okay, and this gives me this equation. The y component would give me another equation. So now look at the y component. AB doesn't have any y component. BC has a y component. So I'll get y component minus VBC cosine theta. And then on the other side of the equation, VAC has a y component, minus VAC AY. Right? Okay. So what do we get from here? VBC equals VAC over cosine of theta, right? So this is the other equation that we got, right? And now you can substitute the value of BC from there to here. I'll just, ये देख लें, BC की वैल्यू वहां से, ये BC है, सॉरी, BC की वैल्यू यहां से यहां पे, तो what you would get is after some simplification, well, just rearrangement, actually, no real simplification, VAB over VAC is equal to tangent of theta. So this example, I know that this actually is not very simple to comprehend, but this was to give you an idea that relative velocity, it gets a little bit, so it's important that you know how to deal with it in 2 dimensions. Okay, the purpose of this example was that you are able to decipher 2-dimensional cases. And if we have 5 more minutes, and I would like to just repeat one of the problems that we already did in recitation, I guess 4, the third problem. You remember the problem?
I had another question. मैंने आपसे पूछना था कि जो क्विज है ट्यूसडे को वो लिनियर है, मतलब आप मतलब एक क्वेश्चन जब तक आप पहले क्वेश्चन का आंसर नहीं लिखते, यू कांट गेट टू द नेक्स्ट क्वेश्चन। तो मतलब इसके अंदर ये इशू नहीं होगा कि अगर हमें पहला क्वेश्चन नहीं आता तो हम लोग उसी पे बैठे रहेंगे एंड वी विल वेस्ट आवर टाइम्स और आगे वाले क्वेश्चंस नहीं हो पाएंगे?
जी बिल्कुल, you would waste your 5 to 10 minutes on that, the time that is allocated for that question. And
वेस्ट एज इन वो क्वेश्चन समझ नहीं आ रहा तो फिर तो टाइम वेस्ट होगा ना, कि हम वो क्वेश्चन कर भी नहीं रहे एंड वी कांट मूव ऑन टू द नेक्स्ट क्वेश्चन ईदर।
Yeah, but unfortunately that's the only way we can do to stop division of labor.
पर सर वो मैंने आपसे पूछा था कि क्वेश्चंस मतलब वो नॉर्मल क्वेश्चंस होते हैं या एमसीक्यूज टाइप होते हैं?
वो डिफरेंट एनालिटिकल भी कुछ हो सकते हैं, थोड़े बहुत एमसीक्यूज भी हो सकते हैं, शॉर्ट आंसर्स भी हो सकते हैं, रीजनिंग के भी हो सकते हैं।
थैंक यू सर।
So we have, let me finish this, procedural questions afterwards, please. Let me finish with this example and then you can ask all your questions. Okay, so we had this problem in the recitation that we have a car which is moving at 150 kilometers, 156 kilometers an hour, and then we have an aircraft which is moving at 208 kilometers an hour, and we want to drop a package that we wish to land in the car. Okay, and the unknown in this case was D. At what horizontal distance, at what ground position of the aircraft should we release the packet so that it successfully lands inside the car? That was the question. And we are also given the height of the aircraft. It's flying at 78 meters height. All right. So now let's solve it using the relative velocity. The last time we didn't know relative velocity at that point, and we used the position vectors to solve it. But let's look at the same problem from the position velocity point of view. So can someone help me find out if I know the height of this object? Although it's initially when it's released, because there is a horizontal speed, when the packet would be released from the aircraft, it would be traveling initially horizontally at 208 kilometers and would have 0 vertical velocity. You agree on that?
Yes, sir.
Yeah.
So how long would it take to hit the ground? Doesn't matter where. This was our first lesson.
Free fall से होगा ना, through मतलब नीचे free fall.
So all the distance that
We
it
have
has
the
to cover
distance and we have the
is half gt squared, right? That's it. That's all the distance that it has to cover, right?
Yes, sir.
Right? So now we have G and we have H. Can we calculate T?
Yes, sir.
That's about, I guess, 15.6 seconds or something. And now, the only question is that both of these objects are moving. And all we have to figure out is this horizontal distance, and both the objects are moving horizontally. So what is their relative speed? What is V relative? The initial
time is not 8.6, वो time का square है.
The time is 3.997.
Okay. जो भी होगा, you'll figure that out. I don't know. You'll figure out time, right? Or if somebody has figured out, just give it to me.
3.99.
3.99 seconds. Okay, so this is the time that would take the package to just land on ground. Doesn't matter where you release it and what horizontal speed the aircraft has. It does not depend on that, right? So that's the time it's going to take to land on ground. So if that is the case, all we need to worry about is to find out if they were both in line. Now you can take them. If the car and the aircraft were both in line, how long would it take, or what distance would it take travel in these seconds to hit the car? And then you can figure out from the relative velocity the initial speed of the packet, which is the same as the speed of the aircraft minus the speed of the car. So this would give you the V relative, and then D is simply V relative times T. And if you remember doing the same problem when we use the position vectors, the expression that we got looked like this. And I hinted about the relative velocity coming into play. We arrived at this answer using the position vectors, but you could just directly introduce it, right? So using relative velocity makes problems simpler and easier. And we obtained the time using the same thing, just comparing the X components.
Sir, can you please explain that again?
Which part?
ये जो आपने equation UA minus UC वाली derive की है.
Do you remember the recitation? If you go back and look up your recitation notes, at some point when we were calculating D, the final answer was this: the speed of the aircraft minus the speed of the car times time T.
नहीं, मैं उसकी बात करी जो आपने ऊपर V equals to ये वाली ऊपर जो निकाली है.
ये
इससे
वाली
बिल्कुल ऊपर। हाँ जी
ये वाली
एग्जैक्टली ये बात।
ये तो
Yes.
relative speed निकाली है ना. If two objects are moving in the same direction horizontally, two different velocities, what would be the relative speed? The difference of their speeds. यही तो हमने आज के लेसन में किया है.
आपने इसमें ओरिजिन को वो पॉइंट ऑब्जर्व करने वाला पॉइंट समझा हुआ है?
देखिए इसको अब मैंने इसमें लिया ही नहीं है कोऑर्डिनेट सिस्टम. ओरिजिन को जो मर्जी लें. इतनी so simple problem. Doesn't matter where you take the origin. It's rectilinear motion in a line. No worry about the coordinates.
Sorry. Thank you, sir.
Okay, thank you very much. Now, any questions that you have about other processes?